And there I am. Hello. Basically, we'll be doing some live measurements and a talk about how to use AFM for polymer characterization. This is the star of the show, the NX10. This is the instrument I will be using today. And I will explain more about the hardware when we get to that. For now, let's just show you my presentation. So just give me 1 minute. Okay, yeah, that took a minute, but yeah, here we are. As Jacina already pointed out, that I will be talking about pinpointing the polymers and nanomechanical characterization of functional polymer blends. So overview of today's webinar is I will start with the introduction to polymer material design, some of the applications, structure scales in polymers, and then I will talk about the two most commonly used classes of polymer materials, namely polymer composites and polymer blends. And then finally, I will also talk about a bit sample preparation for AFM. During these two points, I will show you some examples how AFM can be used for characterizing the polymer and why AFM basically, why as well. In the second part, I will switch to the pinpoint mode of AFM on our NX10. This is a very nice picture of our NX10 system, which is our small sample research AFM tool. I will talk some basics about pinpoint and then move to live demonstration of the instrument and measurements. I will conduct nanomechanical characterization on a polymer sample and conductivity imaging using pinpoint. So
sorry for the interruption, Rolf, but your screen is cut, so let me try to fix it for you. 1 moment, please.
So a little overview about polymers and its applications. Basically, applications of polymers are too numerous to list. I've made kind of an overview of major industries and application with some examples. For example, in automobile, aerospace, industries, renewable energy, and of course, additive manufacturing. In renewable energy, especially in windmills, these modern windmill design probably would not have been so efficient without polymer-based composite materials. In these industries, the polymers are used as structural components. There are some cars which are almost entirely made of composites. Lubricants, coatings, paints, and adhesives. Examples are, of course, rubber tires and composites. In the electronics industry, there are many devices which have polymers as active optoelectronic components, so not just structural chassis or body of a cell phone, for example, but really the active component. And perhaps the most common example which everyone can relate to is the OLED displays. I've shown one here. And then there is one big user of polymers is biomedical industry, where they are making a real impact in drug delivery and biocompatible materials, such as sutures and bone replacement materials and so forth. But in most cases, these are specialized molecules developed especially for the applications. So they are not polypropylene or common commodity plastics. So very similar to biomolecules such as proteins and DNA, there is a hierarchy of structures in polymer materials. So we start at the bottom of the hierarchy. There's the primary structure, the chemistry of the polymer, where we have certain monomers, we polymerize them, and we get a long chain macromolecule. But there are also higher levels of structures, such as chain architecture and configuration. And then there can be blends and composites. In material design, or when one is developing a polymer for a certain application, basically one can do it at any of these levels in most cases. process complexity. For example, if one is developing a polymer for high impact application, and we would like to use a specialized monomer for that, there is one polymer called ABS, acrylonitrile butadiene styrene. So there are 3 monomers in there, and we make a polymer chain out of it. And eventually, the final product is a high impact resistance polymer. But doing chemistry is a very complex process on an industrial scale. It takes a lot of resources to do this. But if we go to the higher level, we can simply take 2 more common polymers, such as polystyrene, and blend it with the thermoplastic elastomer or some rubber, and we will get similar properties to ABS. And this is easier to do at this scale, this level of the hierarchy. There are a couple of quite old but very instructive articles if you want to learn more about these ideas. Basically, I've simplified this hierarchy, so not everyone here is a polymer expert, so I didn't want to spend too much time on it. But the point I want to deliver is polymer material design covers large length scales. So they go from single molecule up to blends and composites, which I will talk about more in a minute. So this is where most of the material design in polymer industry happen. Not so much at the chemistry. Only the research labs and bioapplication work at this scale, mostly. So starting from the smallest scale, I want to mention, Justina already did, but here I can also put in a few words. My colleague Vladimir Korolkov will give a webinar on nailing down Teflon molecules, high resolution AFM imaging for polymer science. And he took these beautiful images of a Teflon film at larger scales, from starting from about 100 micrometers, zooming in on 250 nanometers, and then about 35 by 35 nanometer scan. And here you can see individual polymer chains. And these images were acquired on Park System Tools. He will give a repeat webinar on 28th of January next year. So make sure you check that website and register. But I will not talk about molecular scale imaging. What I'm more interested to talk about is polymer composites. These are basically polymer matrices reinforced with particles, such as fibers, and then we have a matrix, and we reinforce them, and then the composite material has basically the better of both worlds. It has improved mechanical characteristics better than any of these 2 materials alone can offer. And these materials are often used in where applications where high mechanical performance is required, such as the windmill and also in aerospace industry. When one is designing a composite, there are a few key performance parameters that a materials designer looks at. One is particle morphology, so you can have more or less spherical particles, flake-like particles, fibers. These are quite common. And then laminar composites. The second key performance parameter is distribution of the particles. So they have to be homogeneously distributed in the matrix. And then there is the binding between the particle and the matrix. If they don't bind well together, you can't expect high mechanical performance, because essentially then these particles become a failure point, nucleation points for crack propagation, and so these materials fail then. So how can AFM help characterize such materials? This is one example how AFM helps characterize composites. So what I have here is a schematic diagram on the left, and on the right I have a modulus image of a system that is shown in the schematic diagram. We have a rubber matrix, and then a zinc oxide particle is embedded in the matrix. Zinc oxide is a very common additive in the rubber industry. Almost all rubber compounds contain zinc oxide. Rubber chemistry cannot go forward with zinc oxide, and this is the cheapest and the most common one. So there is this particle embedded in the matrix, and there is this interface region between the particle and the matrix. And this is a modulus image, a nanomechanical property map, and we see this particle embedded in a homogeneous rubber matrix, and we can, at the edges, we can see this interfacial region. And I don't know of any technique that can access experimentally this interfacial region between the matrix and the particle in a solid polymer. So AFM offers direct characterization of interface between single particle and polymer matrix. And of course, I don't show it here, but topography can also show the distribution of such particles in a matrix. Moving on to polymer blends, they are slightly different from matrices because in composites, the added particles are often not polymers. They are ceramics in most cases, but one can also blend polymer with another polymer. This is done basically to improve mechanical properties, but the problem is not all polymers are mutually miscible. So you can have a miscible polymer blend or an immiscible one, and if the two polymers are miscible, you will have an interface between them which is spread over a large distance. And if the two polymer components of the blend are immiscible, you will have larger domains, but the interface between them will be sharp. And depending on your application, it depends whether one wants a sharp interface or a more diffused interface. Building on the example that I gave you earlier, for example, if we are designing a polymer blend, which is a high impact resistant material, we can use polystyrene and add a butadiene rubber to it. But if the interface is sharp between the domains of butadiene and polystyrene, these interface, basically, this is where the polymer starts to rupture. This is where the failure of a mechanical part starts. Typical domain sizes cover quite a large range of length scale. They can be anywhere from 20 nanometers to 100 micrometers. And again, the key performance parameters for polymer blends are very similar to composites: domain morphology, their distribution, and of course miscibility. And this is judged by the interface between the two. And AFM is a powerful tool for measuring all of the key parameters. So within one tool, you can have basically all the information one needs to develop a polymer material. And AFM typically works in tandem with a bulk mechanical property characterizer, such as a universal testing machine. This is an example of a binary blend of polystyrene and polybutadiene. These two polymers were dissolved in a solution and deposited on a silicon wafer surface. These images were acquired in pinpoint nanomechanical mode, which I will talk about further on in the talk, on an NX10 system by Park. The rightmost image is the height image. We already see some of the morphology here. The middle is adhesion force image, and we clearly see that there are domains which are less adhesive than the matrix. And then we have our modulus as well, of course. So these properties are readily imaged in pinpoint AFM. There are other channels as well. For simplicity, I'm only showing 3 of them. You can also have stiffness, energy dissipation, and deformation of individual domains. And this image is about 10 by 10 micrometers. Recently, some of our customers were interested in how sample preparation for polymer occurs for an AFM characterization. It really depends on what sort of samples you have, how your material looks like before you prepare it for AFM. The general goal I can define is to obtain a flat topography. AFM essentially is a surface characterization method, and it might be interesting to get as flat a topography as one can. The simplest method is simply take a razor blade and cut polymer sample and put it under an AFM. I have done it, and in some cases it works, but the topography is typically very rough on the scale of 1 to 2 micrometers with the normal razor blade. But ultra microtome is let's say a specialized blade which helps us to obtain a flatter topography. And one can have several cross sections of a polymer, and one can image it so one can get an idea what's the distribution of my particles if I go deeper into the bulk. Another popular method for polymer sample preparation for AFM is solution casting. So basically dissolve the polymer in some solvent, either spin coated on a surface or drop casting. If the solvent is highly volatile, basically it will evaporate and you will be left behind with the polymer. Substrate, excuse me. The substrate that are used are silicon wafer, mica, and highly oriented pyrolytic graphite. And here again, the goal is which substrate to choose. The goal is to have as flat a surface as possible, so there is minimum interference by topography, and you can measure mechanical properties. And there's another method of sample preparation is resin embedded polishing. So basically we embed our polymer of interest in an epoxy resin and then polish this to obtain a flat topography. Again, the overall goal is to get a flat topography. During some of these preparation methods, the triboelectricity produces electrical charges, and this creates problem for the cantilever tip, and it has problem engaging on the polymer. So it is recommended that the sample is grounded when we put it in an AFM, and for this one can use conductive adhesive. We also have our on our NX20 tool ionizers, which help with the most challenging of the samples. Okay, now moving on to pinpoint mode AFM. Starting with the basics, this is the force distance curve plot between the force that the cantilever measure and the Z displacement of the Z piezo in an AFM. The red curve is the approach curve. So we are approaching, we're getting closer to the sample, and at some point our cantilever snaps in and contacts the sample. Then we apply a certain force up to a set point, which we basically specify. We tell the softwares to go up to 20-25 nanonewtons of force, and then the Z piezo starts returning back. This is the blue curve. And then suddenly it snaps out of the surface and loses contact. And this snap out point is the adhesion force. That's how much adhesion is between a cantilever a tip and surface. So what information we can get from an FD curve? The slope gives us stiffness and modulus. Topography is acquired at the set point force. One can also map adhesion force. So basically at this point, adhesion energy, the area between these two curves, this region, energy dissipation. Since for some samples, the approach and retract curves they don't match very well. So one can also measure the area between them, and of course, deformation. From the force distance curve, we go to mapping. And the best way to show this, how mapping works, is basically to show an animation. So we have our X, Y, and Z scanner, our AFM sample, and the cantilever. And basically this force distance curve is repeated on each point of an imaging region. And if our sample is inhomogeneous, we will have different force distance curves. So you see 1, 2, and these three are, they look very different. If we have a hard and firm part on our surface, this is how the force distance curve will look. Soft and adhesive will have slope like this. So that's the basic, and this is how pinpoint mode works. On each point on each pixel in our image, we get one force distance curve with a linear motion, and we generate maps of topography and modulus, adhesion force, and etc. Okay, now I would like to show you a live measurement that I have running here. So let me change the screen first. Okay, so this is the Smart Scan software, and you see already that I have a measurement running on a polystyrene and low density polyethylene blend deposited with solution processing on a silicon wafer. And you see here in the optical image, my cantilever is engaged on the surface and it's scanning. There are these channels that we talked about. We have Z height. Right now, I'm scanning a 3 by 3 micrometer area. The next channel I'm showing is deformation. I have adhesion force, and of course, the modulus calculated from this. The image we see here is only the height image. If we want to look at the other channels in image format and not only this spectroscopy view, we have to click here to go to scan data, and we can select which channels we want to show. The available channel that the software will record are shown at the bottom. We have Z height forward, backward, adhesion, modulus, and deformation forward and backward. So we can show them here. Z height, deformation. So you can, if you want to correlate two images as you are acquiring an image, you can put them side by side. And of course, you can add more channels. Basically, you can add all of them, but you have to use these arrows to navigate between them. So we see already that our height and deformation images look quite nice. We see there are certain regions which deform more than others. And of course, we are also measuring the modulus of our samples. Let me change it here as well. So you can read off the modulus values live, but of course, this data will be saved. So I have this running already. It's on repeat, but I think I have shown you that this pinpoint mode can acquire nanomechanical properties. Oh, by the way, I'm sorry, I forgot to mention this. This is the live force distance curve that it's acquiring at each point as the cantilever is moving. If you would like to take a look at a certain force distance curve, what I like to do is simply stop by clicking this hold button and zoom in, see if my force distance curve is looking okay. Then I can uncheck the hold button. When I check the hold button, it doesn't stop acquiring the image. It just keeps on going. It just put this display of a force distance curve on hold. I like this feature when I'm optimizing my image before spending any time to acquire it. I think we don't need to save this image, so I can cancel. So this way I can show you how to set up a measurement. My cantilever jumps to the start position. So this blue pointer here shows me my cantilever position. So basically, to do pinpoint, we first have to select contact mode. It's an advanced mode of contact. And then we have to turn on the pinpoint spectroscopy. And here there are some parameters that are important for pinpoint mode imaging. We set the speed. This is the Z speed with which the cantilever moves towards and out of the surface. We can split it and have different up and down speed, but let's just keep it at 20 micrometers per second at this point. There's the set point. You can have the direct force in absolute units, or one can normalize it and look at in terms of volt signals. There are some other parameters in, if you click the details button, there are other parameters which allow you to have more control on your pinpoint imaging. Minimum baseline is basically this baseline that software needs to calculate modulus and all these other images. So you can set it to a smaller number. And you see my baseline has reduced. Oh, yep. Okay. Yes. Now it is reduced, but it may be a bit too short because of this blue curve. As you see, it might be, we need it to be a little bit further. So 20 nanometers is okay. That looks better. There are some other parameters here, but I won't go over on all of them. Here is the modulus related parameters. You can select which model your polymer fits and which model you want to use to calculate the modulus. A tip radius goes in. I have a number 30 nanometer. I'm not exactly sure. I have not calibrated the tip radius. I don't know if this number is true or not. So my modulus values might be a bit off, but for demonstration, I think it's fine. We leave it at DMT with 30 nanometers, click apply. And once we are sure that our force distance curve looks okay, we can click the pinpoint scan, click apply. Then it starts scanning our polymer sample here. And of course, you can add extra channels. Pinpoint mode offers up to 8 unique information channels. Right now I have height, adhesion force, modulus, and deformation selected. But there are all these information channels that one can use and acquire simultaneously with modulus. For example, in the next measurement, I will show you that one can do pinpoint conductive AFM. So for that, we need to have the current channel as well. So I simply add current channel, or if this list is too long, you can search for it. Click it, add, and then click apply. Then you will have another channel here. So one can select up to 8 channels. Excuse me. And yeah, so I think this is fine. I have demonstrated that we can use a pinpoint to do nanomechanical characterization of polymer blends. And that's our sample here. Moving back to the presentation, we are back at the presentation. So I've shown you quantitative nanomechanical mapping imaging of pinpoint. I will also show you the hardware in the next measurement. But first I want to talk a little bit about contact mechanics. Why these are needed. Basically, the force distance curve is it only measures stiffness. We need to convert stiffness to a modulus number. We need to use contact mechanics models. The simplest one is the Hertz model. It makes some assumptions that basically this contact between our surface and the tip is adhesionless, it's frictionless, and the two materials of the tip and the sample are homogeneous half spaces. So basically they extend infinitely. So these are theoretical assumptions. And the deformation is small and elastic. So there is no energy loss there. These are quite strict assumptions, and as you realize that these might not be this might not be a very good model because there is no contact which is absolutely frictionless or adhesionless. But for some cases, Hertz model actually works fine enough. There are more complicated models such as the Jaguin-Muller-Toporov, shortly called the DMT. We've seen it in the software a little while ago. I was using this model. It's used for stiff materials with long-range adhesion. So this model actually takes into account adhesion, unlike the Hertz model. And then there is the Johnson-Kendall-Roberts model, the JKR. It's mostly used for soft materials with short-range DC forces. So basically, JKR and DMT are two extremes of a spectrum, and your sample can lie anywhere in between. And if you are interested in quantitative measurements, you might need to take into account both of them. The reason I'm talking about contact mechanics is that understanding a little bit about contact mechanics helps with the tip selection as well. The goal is to have a detectable but small deformations on the order of a couple of nanometers, and the deformation should be smaller than the tip diameter. And actually, it's with pinpoint and nanomechanical mapping, it's not recommended to use a very sharp tip because within a few scan lines, they will become blunt. And so, yeah, the tip shape changes quite a lot. The cantilever I was using was an SDR30. This had a starting tip radius about 30 nanometers, but I have been using this for quite some time. So it might be even more, even a larger tip. The second point is that the spring constant of the cantilever. If you choose a high spring constant, it means you can deform the sample more, but this also means you will have a low force sensitivity. So for detecting adhesion force, if you use very stiff cantilevers, your sensitivity might not be enough to detect the force at all. So there has to be kind of a balance between these two. A general rule of thumb is to use soft cantilevers for soft sample and vice versa. So there is really no one size that fits all. One has to play around with some probes and models a little bit to get to the nanomechanical properties. I want to list some of the advantages of pinpoint. It offers direct control of normal force and the contact time. This will be important in what I'm going to talk about next, since for conductive pinpoint, we need to stay in contact with the surface for a little longer. The motion of Z piezo is linear. It's not a sinusoidal motion. It gives you quantitative nanomechanical data, as I have already demonstrated. You can choose up to 8 information channels, so this allows you customizability. Part system doesn't offer it as a separate mode. For conductive pinpoint, you have to buy it separately. It's one package. There's extra hardware for conductive pinpoint, which I will show you shortly. But there is no locks and bounds in the software. You can freely change and choose any channels that you want to record simultaneously with the nanomechanical data topography. And of course, since the cantilever is moving only in Z direction and it only moves XY when it's disengaged from the surface, it eliminates lateral forces. And this is another example of a polymer. I like these images a lot. This is a block copolymer in a rubber matrix. So this region around this central feature is a rubber matrix, and this is a block copolymer within, which is phase separated. We have adhesion energy and modulus. For functional properties imaging, using pinpoint, as I said, we need to use holding time. So basically, we engage on the surface and keep the cantilever there. This is a force time plot, schematic one. So it's basically the same data as we acquire in force distance curve, but I plotted it against time instead of distance. So we approach on the surface, we keep the set point force, stay on the surface for a certain time, and then we withdraw from the surface. And during this holding time, we acquire current signal, or there are some other possibilities that I list here. We can do pinpoint piezo response force microscopy, pinpoint PFM. We can do conductive AFM with pinpoint. This I will show you next. And then there is SSRM as well. This is typically not used with polymers, but some of you might be interested in it. And I want to stress that this is simultaneous functional properties imaging. So some examples of these functional properties imaging on polymer samples. A very common challenge in conductive AFM and conventional PFM is the wearing off of the conductive platinum iridium coating from the tip. And once this conductive coating is rubbed off, your cantilever is no longer conductive and will lose signal. I've seen samples where after a couple of scan lines, we'll lose signal in the conventional conductive AFM. But with pinpoint PFM, I demonstrate here. This is PVDF fibrous membrane. This is a height channel, PFM amplitude, and PFM phase. So topography is acquired at set point force. We hold the tip on the surface, acquire amplitude and phase. And another example with the DNA molecule modified with cytosine silver complex. And this is a pinpoint height image, and this is the corresponding current image. And the pinpoint solved this problem of tip wear by reducing lateral forces. As the cantilever is only moving in the Z direction, there is no wear of conductive coating from the tip. So switching back to the live measurements, and now I would like to show you some of the hardware, how to change the cantilever, and I will switch to a new sample. So let me do that now. Okay. So first I have to withdraw my cantilever from the measurement I'm already doing. Let's see all. So this is the acoustic enclosure. And as you can see, my tip is still withdrawing, but that's enough, so I can stop it. It's really easy to handle the hardware of this tool. This is the scan head that we use. That's a pre-mounted cantilever right there. I don't know if you can see it. I will change this to a conductive cantilever now. And additionally, I have this head extension module, which is for conductive AFM, which I need for the conductive AFM that I have to show you now. This is basically a preamplifier that we will need now. So I have to change the cantilever. It's really easy with these pre-mounted cantilevers. They're basically just already mounted on a metal chip and magnetically held in place. So I can use simply my hands. I don't even need to use tweezers. But let me quickly change the cantilever. This is a conductive CDT NCHR cantilever, and as you see, there is already a tiny cable with it, which I need to connect to my head extension module so I can read the current from the cantilever. I can show you a bit closer. So this yellow cable is connected to the cantilever. It goes in the conductive AFM head extension module. I also need to change my sample. Oops. Then I simply slide in the scanning head, lock it in place, and I have to attach this head extension module to the microscope so it can read the signal. And basically, then I have to do the laser alignment procedure. And if you look to my software screen that I hope you can see, there is this optical view. First, I have to bring the cantilever into focus. Maybe position it in the center. Then I can change the light setting by increasing the exposure and reducing the light. This setting allow to see me my laser here. So we already see a faint shadow of the laser. And there it is. With the pre-mounted cantilever, it's really easy because the laser is never too far off. And I can position the laser spot in the center of the PSPD by using the 2 screws on the head. It doesn't have to be perfectly 0.00. As soon as you see that this spot has turned green, you're good to go. So once I have done this, I can close the acoustic enclosure, and the rest I can control at the software. So I will turn off my camera now. And yeah, again, so we select contact. And for now, to begin with, I would like to turn off the pinpoint scanning. So right now it's in normal contact mode, but I won't image because I want to protect my tip. So I set a scan size of 0. I can clear the previous images from here. And then basically I will set my, and I have to change my cantilever type as well. So there is this list of cantilevers. It's a database. So you just tell the software which cantilever you are using, and it will prepare your AFM for that cantilever. So once I have this, I can simply click approach. So this yellow bar here represents the Z stage. And as you can see, it's moving towards my sample. We will also see that the sample will slowly start to come into focus in the optical view here. Perhaps I retracted a bit too much. If this is too slow, what we can do is, perhaps I can take this opportunity to show you. We can go to the approach settings and increase the speed. And click approach again, and now it's moving with twice as much speed. But there's no worry, you shouldn't, it won't crash into the surface. As soon as it comes close enough to the surface, it will switch to an incremental approach procedure, which is designed to protect the tip crash. And there we go, incremental approach. Now it's slower It's slowly moving towards the sample. My set point is a bit too low. Yeah, I was still far away from the surface. And I think now we are on the surface because you see in the optical view, we have the sample surface almost in focus. At this point, what I would like to show you is our current amplifier settings. So right now I'm using an internal DC current amplifier. I will set the gain to 10 to the power 6. And if there is any offset, there is any residual current, excuse me, you can enter the value here to offset that. But quickly moving to pinpoint spectroscopy, start FD. Here comes this parameter, the average time. This is basically the holding time that we would like our tip to stay on the surface. So let's just start with the number 4 millisecond. And you can also visualize this here. So right now it's just a force distance curve as we have seen before. But we can plot the force versus time. And as you can see, this is something similar to what I shown you before. We come in contact, increase to the set point force, hold the cantilever there, and then retract. I can start the pinpoint scan. And now I can tell my software to start scanning, for example, 2 by 2 micrometers. Then I can apply, let's start with the 1 volt bias. Do I have a current image here? Yes, there we go. So let's put this here. And you can already see that it's acquiring, let's start the scan. It's acquiring topography, deformation, adhesion force, as we've seen before in the case of nanomechanical imaging. But now we also have a current channel here. The imaging is a bit slower now because we are holding the cantilever 4 milliseconds on each pixel. So that obviously makes the process a bit slower, but you see a very clean current image. And this will be very stable over the time because there are no lateral forces there. If you want to correlate the current data, you can go to scan data, select Z height, current, and yeah, you can correlate it once this image starts forming. But yeah, I think it's pretty clear from this channels here that we can acquire very nicely and very easily conductive maps with the pinpoint as well. So what I can do now is cancel this image, and I can switch back to my presentation. All right. Yeah, so I have demonstrated pinpoint conductive imaging. It was only a few lines, but in the interest of time, I didn't take a complete image, but you could see already from the data that we were acquiring that it was a very nice conductivity line scans. And coming to end, to summarize, I have shown you that Park Systems AFM can provide direct images of polymers from a single macromolecules to hundreds of micrometers. Polymer blends and composite, we talked about, it's an important class of materials. It has many, many applications, too many to list. But in both of these classes, key parameters such as domain morphology or particle morphology in case of composites, their distribution and the interface between the two. This is really important because I don't think there is any other method that can do this. We can characterize all of these in basically one go using AFMs. We can acquire quantitative nanomechanical data using pinpoint imaging, for example, adhesion, deformation, modulus, stiffness. This is obviously not an exhaustive list. And finally, I demonstrated to you the functional properties mapping, such as piezo response. I shown you example and demonstrated conductivity imaging using pinpoint. And with that, I would like to end here. Thank you for joining our webinar. Thank you very much for your attention. If you have any questions, please let me know and talk to us. Visit our website to learn more. Talk to us if you want to learn more about your application and how AFM can help you. Thank you.